In this next section, we're going to talk about the Schrödinger equation just a little bit, but mainly look at the consequences of it. This section is 40.7. One can say, as they did at that time, the year was 1925, and the question was this. In the past, we had a particle that moved along. That particle had a mass, and it may have a charge, and it would move with some velocity, and it was located at some position, x, y, and z. And this motion was described by Newton's equations. But now the particle is not just in one place. It's spread out. It acts like a wave, and as the electron goes around the proton, it is actually a wave that's traveling around. How do we describe the motion of particles now on the small scale where they're behaving as waves? Well, that is done by the Schrödinger equation, and equivalently the Heisenberg equation would do the same thing. And this equation is really too complex to describe at this level of the physics course, except to say it's a complex, very complicated partial differential equation involving position and the time. But what we can do is talk about some of the results of that equation and what orbits are allowed in an atom. Now remember, the electrons are going to fill up these levels, and so you can only have certain electrons in certain levels, and what we're going to do is talk about that, which gives us the basis for chemistry, and that's really the connection we're trying to make here, is talk about the results. The Schrödinger equation solution gives the following energy values: that the principal quantum number, remember this is called the principal quantum number, right there it is right there, N, for the angular momentum that we just spoke about, can be 1, 2, 3, or any higher integer. Those are the various levels for the principal quantum number. But having that principal quantum number, you can have these quantum numbers are denoted by names. This is called the K shell, the L shell, and these are capital letters, the M shell. And this comes from previous designations before people understood what these various levels or shells were doing. They had named them the K, L, M, and so forth shells. Now, within each of these shells, you can have different angular momenta. And the angular momenta, L, can equal the value 0, because you can have no angular momentum at all, or 1, or 2, or 3, up to n minus 1 times h bar. Remember, the angular momentum is a multiple of h bar. So it can be 0 h bar, 1 h bar, 2 h bar, 3 h bar, and if I'm in, say, the L shell, I could go up to 2 minus 1. That would be 1. That would be the highest I could get for the L shell in giving me my value of L. The actual angular momentum is given by a more complex expression, L times L plus 1 square root times h over 2 pi, or h bar. Let's write it as h bar. This is because the angular momentum, which is L, actually kind of wobbles around, so it has a slightly greater value than you might think. This is a less important equation here, so I would say you can neglect it for the moment. Now, these various orbital angular momentum numbers are also given names. They're called the S, P, D, F, G, and H, and then it goes alphabetical. S, P, D, F, and then the next one be G, H, and so forth. These are the letters given to the angular momentum. So I can talk about the K shell and an angular momentum of an S electron, or an M shell and a P electron, which means that the angular momentum would be 1. Therefore, we have all these angular momenta that go from minus L up to plus L that have another quantum number associated with them called the magnetic quantum number. And these were discovered having to do with the magnetic field, and it's actually the z component of the angular momentum, which can aim straight up or at different angles, but it also is quantized and can only be from a plus L to a minus L times h bar. So these give different orbits within that atom also. Well, let me stop just a minute and back up. Say, okay, where are we? In a given orbit, we have a given value of n. N might be, say, 4 right here. So n is equal to 4, and this would be called an n level. Now, within that n level, I can have different angular momenta. I can have angular momenta that would go from 0 up to 4 minus 1, which would be up to 3. So I can have S, P, D, and F electrons. All 4 of these angular momenta can be present. Now, each one of these can also have different states for the electron. The angular momentum can, in the z component, can be, say for 3, could be 3, 2, 1, 0, minus 1, minus 2, minus 3 times h bar. So this gives us another set of orbits that are possible. Now let me pull this page up just a little bit higher. And this is somewhat complex, but it's something that you will be exposed to in your chemistry classes. So it's something you should be familiar with. This is known to correspond to the z component of angular momentum, as I just said. Then we have a final splitting of the energy levels that's associated with the spin of the electron, because the electron can spin up or it can spin down. So that gives us 2 more of those. So now we can say, how many orbits do we have? Well, the maximum number of electrons in a shell are 2 times 2L plus 1. This comes from the 2 of the spin up and spin down, and we have 2L plus 1 that can go in those orbits. And so, for example, we could look at the orbit and see if you can calculate this. In the n equals to 2 orbit, we could have L is equal to 1, because that's 1 less than the value of n, and we could have 5 electrons. And therefore, the 5th electron could be the 2p5 level. That's for the n is the 2, so this is written as 2. The n would be the first. Then you would have the p level, meaning the angular momentum L is equal to 1, which is okay because L has to be 1 less than n from our last equation. And this would be called the configuration of carbon, for example. You can have in the first orbit, with no angular momentum, 2 electrons, 1 spinning up and 1 spinning down. Then in the next orbit, you could have no angular momentum, which is an s orbit, and I could put 2 electrons in that. Then the next one, I could have the 2 level, and I could have a p orbit, where angular momentum L is equal to 1. And I could put 2 electrons in that, and I would have 2, 2, and 2. That would give me 6 electrons, which would give me a configuration of what carbon normally is. So this type of understanding of the configurations is something we're not really emphasizing here, but in chemistry, it's of the greatest importance. And so since we need to prepare you for those chemistry courses, this is what you should understand, at least at this level, and it will be explained in more detail in your chemistry class or your quantum mechanics classes that you have in physics. See if you can describe these and use those equations.